In this video, I'm going to be going through part C of question 3 of the tutorial. And in this part of the question, we're going to compute the Wasserstein distance. Throughout the video, I'm going to use my Australian pronunciation. So I'm just going to be saying Wasserstein distance. Now, just like the previous parts of the question, I think the easiest way to go about this is to take the formula piece by piece, figure out what the values are, and then put them all back together at the end to get the answer. So why don't we go ahead and start by looking at this first term here. So we need the L2 norm of the difference between the mu1 and mu2 mean vectors. So we can see the mean vectors over here. So mu1 minus mu2 simply evaluates to 1, 0. And to get the squared L2 norm, well, the L2 norm of the 1, 0 vector is just 1. And if we square that, we end up with 1. So that's the first term of the equation done. Let's move on to the next term of the formula. Now you can see that we need the trace of this quantity inside the brackets here. So to do this, I'm going to do all of the trace calculations separately. So I'm going to get the trace of the first covariance matrix, which is simple to read off up here. We can see it would be 0.04 plus 4. Easy. Then I'm going to get the trace of the second covariance matrix in exactly the same way. Now this matrix is the identity matrix, so the trace is 2. Now this third trace is slightly more complicated. So what I'm looking for is the trace of -2, and we've got a matrix multiplication here in the brackets, and we want the square root of that. So let's bring the -2 out of the brackets, and we will find the trace of the product of this multiplication, matrix multiplication, like so. Now E2 is the identity matrix, so inside the brackets here it's simply the covariance matrix for distribution Q. So the next step of this calculation, inside the brackets we will have 0.04 and 4 down in this dimension. Cool. So let's get rid of that power in the next step. So the square root of 0.04 is 0.2. Square root of 4 is 2. So this part of the formula reduces down to -2 times the trace of this matrix in here. And we can see that that will be 0.2 plus 2 comes out to be 2.2. Cool. So now we've actually got all of the things we need for the right-hand side of the equation here. So let's go ahead and put it all together. So we're calculating the W2 distance between Q and P. And note that we've got a square over here. So this is squared. So I'll put the 2 up there. And if I fill in all my values, I end up with 1 plus 4.04 plus 2. And then we need to subtract this final term that we found. So minus 2. In brackets we have our 2.2. So this ends up being, actually I'll get my calculator for this one, 7.04 minus 4.4. Which is 2.64. Now we need to get rid of this squared power over here. So the actual distance comes out to be the square root of 2.64. If we want this down to an actual decimal value, it is approximately 1.62. So just like the KL divergence that we've been looking at in previous parts, this is also a measure of the distance between two probability distributions. Probably the main difference with the Wasserstein distance here and the KL divergence is that this one is symmetric. So you guys probably remember from previous parts or the discussion from in class that the KL divergence is not symmetric. If you want to represent the Q distribution in terms of the P encoding, you're going to get a different answer than if you do vice versa with the KL divergence. So the Wasserstein distance is a true distance metric, whereas the KL divergence is not. When would you use one over the other? Well, it just depends. You might want to use the KL divergence if there is a significant overlap between the two probability distributions. But if you need a true distance metric for whatever your task is, the Wasserstein distance is the one you should be thinking about using.